80 million years ago, a massive colony of dinosaurs was, well, they were essentially buried alive under a mountain of pale white ash in Montana.
Yeah, the mothers, the nests, the unhatched eggs, all of it just entombed in a geological instant.
Right. And when you look at the sheer volume of that ash fallout,
Yeah.
you're looking for a cataclysmic source, right? You're looking for a supervolcano.
Exactly. And geographically speaking, the only suspect massive enough to unleash that kind of hell on Montana is the Yellowstone megacaldera.
Which is sitting just, what, 350 kilometers to the south?
Yeah, about that. But there is a massive problem with that theory.
Right, because according to the standard geological timeline, Yellowstone didn't even exist yet.
Not even close. Standard dating says Yellowstone wouldn't exist for another 80 million years.
So for you listening, think about this. You have a murder scene, right? A mountain of physical evidence, and a primary suspect that supposedly wasn't even born when the crime was committed.
It's essentially the ultimate geological locked room mystery. I mean, if the volcano didn't exist, where did all that ash come from?
Exactly. And if the volcano did exist, what does that mean for our understanding of, well, of time itself?
Right.
So welcome to another deep dive. Today's mission is a really fascinating and frankly, kind of a mind-bending intellectual exercise.
It really is.
We are unpacking a radical alternative geological framework. It's called the Unified Theory of Geologic History, or UTGH.
Proposed by an independent researcher named Daryl Waters.
Yeah. And we need to establish the stakes here immediately.
Oh, absolutely. Because this framework, it doesn't just tweak the edges of modern geology. It strikes at the absolute foundation.
Right. So we are comparing the standard geological model, which is built on, uniformitarianism, this idea that the Earth changes through slow, constant processes over deep time.
Yeah, comparing that with UTGH, which operates entirely on catastrophism.
Which means?
Well, UTGH argues that the major features of the Earth were forged rapidly in a planetary scale disaster.
Right. And just to be completely clear with you listening, our job today is not to take a side.
No, not at all. We aren't here to declare standard geology a lie, and we aren't here to coronate UTGH as the new absolute truth.
Exactly. Our goal is to rigorously explore the physical, the chemical, and the geological evidence presented in this source text.
We are going to strictly apply the scientific method.
Yeah, using formal if this then that logic to test the claims Daryl Waters makes about the fossil record.
Because we have to follow the physical evidence wherever it leads. I mean, even if it leads to some really uncomfortable conclusions about our established timelines.
Okay, so let's start with the weapon itself, right? Yellowstone.
Okay.
If UTGH is going to claim that Yellowstone buried those dinosaurs, we first have to understand how Yellowstone became a megacaldera in this alternative framework.
Right, which requires completely changing how we view the ground beneath our feet.
Yeah, because under UTGH, we aren't standing on a slowly drifting tectonic plate.
No, we are standing on a giant decelerating treadmill.
A decelerating treadmill. Okay, so to understand the mechanics of this treadmill, we need to look at a geological feature known as a hotspot.
Yeah, and this is actually a concept where both the standard model and UTGH, they share a basic physical premise.
Which is rare in this text.
Very rare, yeah. So a hotspot is a fixed plume of incredibly hot mantle material upwelling from deep within the Earth.
It's essentially anchored in place beneath the crust, right?
Exactly, anchored and fixed.
I always picture it like a fixed blowtorch pointing straight up.
Yeah.
And the tectonic plate is like a thick sheet of metal being dragged over that stationary flame.
That's a perfect analogy, because as the plate moves, the blowtorch burns through, right? It leaves a trail of scorch marks across the surface of the plate.
Like volcanoes, calderas, lava fields, things like that.
Yeah, and those scorch marks form what we call a hotspot track.
Because the mantle plume is stationary and the plate is moving.
Right. So that track is a permanent geographical record. It shows you the exact directional heading of the tectonic plate.
But more importantly, for our deep dive today, it provides data on the speed of that plate.
Yes. And here is where the two models completely diverge on how to read that speedometer.
Okay, lay it out for me.
Well, if I look at the standard geological model, it tells me that tectonic plates move at this agonizingly slow, constant speed.
Like, what, 2 to 5 centimeters a year?
Yeah, basically the speed your fingernails grow.
Yeah.
So if I see a really long hotspot track, standard geology says it just took millions and millions of years for the plate to slowly creep over the blowtorch.
Right. Time is the major factor. But UTGH throws that uniformitarian speedometer out entirely, doesn't it?
Completely out the window. The UTGH framework posits that roughly 5,300 years ago, the Earth experienced a singular global rupture event.
And we will get into the exact mechanics of that rupture shortly because it is wild.
Oh, it's intense. But the kinetic consequence of this event was that the Earth's tectonic plates were violently decoupled from the layer beneath them.
So they weren't attached anymore.
Right. They began to literally hydroplane across the globe at terrifying velocities.
Wait, hydroplaning? Like a car on a wet road?
Essentially, yes.
Are we talking like meters per second?
Easily meters per second. But the physics of hydroplaning dictate that without a continuous driving force, the momentum can't last forever.
Right, friction exists.
Exactly. So in the UTGH model, these continents were launched at massive velocities, but they immediately began experiencing kinetic decay.
So they've been decelerating ever since.
Yes, grinding down from meters per day to feet per year, and finally down to that centimeter scale creep we measure today.
Okay, so instead of a constant slow creep for millions of years, UTGH sees this violent shove followed by thousands of years of, like, slamming on the brakes.
That's a great way to put it.
But how do we test which speedometer is correct?
Well, Daryl Waters directs us to look at the physical evidence of two very specific hotspot tracks.
Okay, what's the first one?
First is the Yellowstone track itself. It forms the Snake River Plain, carving through Idaho and ending up in Wyoming.
Right, and how long is that track?
That track is approximately 430 miles long, or about 700 kilometers.
So a 430-mile scorch mark.
Yeah. Now, compare that to a different system entirely, the Reunion Hotspot Track in the Indian Ocean.
Okay.
That was created as the Indian Plate moved over its own mantle plume. And the Reunion Track is immense. It's approximately 2,000 miles long, ending at the massive Deccan Traps in India.
Wow. Okay. So we have a 430-mile track in North America and a 2,000-mile track in the Indian Ocean.
Right.
Standard geology just says the Indian Plate spent way more time over its blowtorch, right? Like 65 million years versus Yellowstone, 16 million years or something.
Yeah, exactly. Standard geology uses time as the variable to explain the difference in distance. It assumes velocity is constant.
But UTGH flips that equation.
It does. In UTGH, the time frame for both tracks is identical.
Because they both started moving at the same time.
Right, after the rupture event 5,300 years ago. Therefore, the variable isn't time, it's velocity.
Ah, I see.
UTGH views those track lengths as direct physical records of kinetic energy and deceleration.
So if they've been moving for the exact same amount of time, the Indian Plate had to be moving vastly faster to carve a 2,000-mile track.
Yes.
While the North American Plate must have been moving much slower to only carve 430 miles.
That is the core deduction, yeah. And the text provides the physical rationale for this, too.
Which is what?
According to the UTGH reconstruction of the rupture, the Indian Plate encountered the Reunion hotspot plume very early in its post-rupture hydroplaning phase.
So it was still moving super fast.
Right, it was carrying massive kinetic energy. Because it was moving at extreme speed, it dragged across the plume rapidly, leaving a colossal 2,000-mile trail.
So moving the metal sheet over the blowtorch really, really fast.
Exactly. Contrast that with the journey of the North American Plate. UTGH argues North America was moving westward, away from the Atlantic rupture zone.
Right.
But the Yellowstone mantle plume is located deep in the western interior of the continent.
Oh, okay. So by the time the western edge of the North American Plate finally ground its way over that specific plume, the plate had traveled an enormous distance.
Yes. It had been fighting friction that entire time.
So it was losing energy.
Massive amounts of energy. By the time it actually hit the Yellowstone hotspot, it had dissipated the vast majority of its kinetic momentum. It had nearly ground to a halt.
Which means it pulled over the Yellowstone blowtorch much, much slower, creating a much shorter scorch mark.
Exactly.
I mean, that makes logical sense, conceptually. But is there any math to back this up? You can't just say one was fast, one was slow, and call it a scientific framework.
Oh, this is where the UTGH framework gets highly analytical. Waters actually calculates the residual hydroplaning velocity of these plates.
Based on what?
Based on their mass, the surface area experiencing friction, and the decay of kinetic energy over time.
Okay, so hard physics.
Yes. And when you run the UTGH mathematical deceleration models, they yield a very specific ratio.
What's the ratio?
The calculated initial velocity of the Indian Plate when it hit its hotspot was roughly 5 times faster than the initial velocity of the North American Plate when it hit Yellowstone.
Wait, a 5-to-1 ratio in velocity?
Yes.
And the Reunion track is 2,000 miles long. The Yellowstone track is 430 miles long.
Which is a ratio of roughly 4.65 to 1, or effectively 5 to 1.
Oh, wow. That is a staggering correlation.
Right. You have two totally independent plates, two separate hotspots, and a theoretical physics calculation of friction and mass.
And the resulting math perfectly matches the physical length of the lava tracks on the Earth's surface.
In the UTGH framework, that's considered conclusive proof. The length of a hotspot track is not an artifact of deep time. It is a literal mathematical speedometer reading.
Of a plate's kinetic decay.
Exactly.
Okay, I'm tracking the physics of the decelerating plates. But this raises a massive mechanical question for me. If North America has lost its momentum and is basically just creeping over this mantle plume in Wyoming, what actually triggers the eruption?
Good question.
Because a blowtorch under a piece of metal just melts a hole. It doesn't spontaneously detonate.
Right.
So what turns Yellowstone into a mega caldera capable of burying dinosaurs 350 kilometers away?
To answer that, we have to look directly into the engine of the UTGH framework.
The rupture event.
Yes. The precise mechanics of this global rupture event. Specifically, we need to understand the concept of a thermal buffer.
Okay, let's get into the mechanics, because if you're going to claim a global cataclysm, the physics have to be ironclad. What exactly ruptured?
According to the source text, prior to 5,300 years ago, the Earth possessed a globally distributed subcrustal water reservoir.
Meaning what exactly?
We are talking about a continuous subterranean ocean trapped between the Earth's solid crust and the hot mantle below.
A subterranean ocean. How deep down are we talking?
The calculated depth is approximately 96.6 kilometers beneath the surface.
Wait, almost 100 kilometers down?
Yeah.
That is an insane depth for water to exist. I mean, if I dig a hole 100 kilometers deep, the heat and pressure would be unimaginable. I'm assuming this wasn't just a dark underground lake you could go scuba diving in.
Not remotely. At a depth of 96.6 kilometers, the lithostatic pressure, which is the sheer crushing weight of the rock above, is roughly 40,000 atmospheres.
40,000 atmospheres.
And the temperature radiating up from the mantle is calculated to be over 1,280 degrees Celsius.
1280 degrees, water boils at 100 degrees. How is it even water anymore? Shouldn't it just be steam?
This is a critical point of physics that's heavily emphasized in the text. When you combine temperatures far above the boiling point with pressures of 40,000 atmospheres, water enters a phase known as a supercritical fluid.
A supercritical fluid. What does that mean, practically?
The supercritical fluid defies our everyday categorizations of matter. It doesn't exist as a liquid, nor does it exist as a gas. It possesses properties of both.
Like what?
It has the density of a liquid, meaning it can exert massive physical force and hold incredible amounts of dissolved minerals in it. But it permeates through porous solids with the effusiveness of a gas.
So it's this ultra-dense, ultra-hot, highly reactive phase of water, just trapped under 100 kilometers of solid rock.
Yes. And because it blanketed the entire globe beneath the crust, this supercritical ocean served a vital thermodynamic function.
Okay, what did it do?
It acted as a global thermal buffer.
Like a layer of insulation.
Exactly. The Earth's core and mantle are generating immense continuous heat, right?
Right.
But before the rupture event, this supercritical water layer was absorbing, distributing, and mitigating that heat. It was physically preventing the 1,200-degree mantle from directly baking the underside of the crust.
Okay, I can see where this is going if that pressure is suddenly released.
The UTGH model posits that a catastrophic fracture propagated through the Earth's crust, and when the crust cracked, the 40,000 atmospheres of confining pressure dropped instantaneously.
And that ultra-dense, supercritical fluid violently flashes into steam.
Yes.
It expands, blasting upward through the crust, lubricating the tectonic plates as it ejects, which causes the hydroplaning we just talked about.
That is the mechanical driver of the tectonic sprint, yes. But let's look at the thermal consequence.
Right, the heat.
What happens to the mantle when that water is suddenly expelled?
The thermal buffer is gone. The insulation is stripped away, so the mantle is suddenly right up against the crust.
It's even more dramatic than that, actually. It's not just the removal of the insulation. It's the removal of the pressure.
The 40,000 atmospheres.
Right. And this triggers a geological process called decompression melting.
Break that down for me. I mean, if I remove pressure, why does something melt? I thought things melt when they get hotter.
We usually think of melting that way, yeah. But melting is a function of both temperature and pressure. Down in the mantle, the rock is incredibly hot. It's easily hot enough to be a liquid at the surface, but it remains solid because the crushing pressure of the crust forces the atoms to stay locked in a crystalline structure.
Oh, so they physically do not have the space to expand into a liquid state.
Precisely. Now imagine you suddenly blast away a 100-kilometer deep layer of high-pressure water.
The pressure on the underlying mantle drops catastrophically in an instant.
Yes. The temperature of the mantle hasn't changed, but its melting point just plummeted.
So the solid rock flashes into liquid magma.
On a continental scale, decompression melting would have triggered massive spontaneous volcanic activity everywhere the crust was fractured.
Wow. Okay, now let's apply this specific physics engine to Yellowstone, because Yellowstone isn't just normal mantle rock, right? We established it's a hot spot.
Right. It's a mantle plume.
So what does that mean in this context?
Well, a mantle plume is an area where a column of material from deep near the Earth's core is rising. It is anomalously hot, vastly hotter than the surrounding mantle rock.
So if releasing the pressure on normal mantle rock causes massive melting, what happens when you instantly release the pressure on a superheated mantle plume?
It goes absolutely ballistic.
It just erupts.
It is the geological equivalent of taking the restrictor plate off a hypercar engine that runs on liquid fire.
Okay, that's a terrifying image.
The UTGH text argues that Yellowstone was not just a typical volcano slowly building up magma over millions of years. It was the apex surface expression of a hyperheated mantle plume.
And it was suddenly catastrophically allowed to vent into this newly fractured, decelerating North American plate.
Exactly. The buffer is gone, the pressure drops, the plume flash melts into a colossal magma chamber, and Yellowstone detonates.
It just explodes.
It erupts with a violence that is almost impossible to comprehend. The initial activation phase of the Yellowstone system, fueled by this decompression melting, produced some of the most voluminous and catastrophic super eruptions in the planet's history.
Okay, so if Yellowstone was firing on all cylinders like that, the immediate question is where all that ejected mass actually landed.
Right.
And, more importantly, who was standing underneath it when it did? Which brings us to the native life of North America.
Yes, it does.
Let's travel about 350 kilometers north of the caldera, up into Montana, to a very famous paleontological site.
We are heading into the Two Medicine Formation, to a location famously known as Egg Mountain.
Egg Mountain, near Choteau, Montana. I mean, if you follow paleontology at all, you know this site.
Absolutely.
It was excavated by Jack Horner, right? And the discoveries there fundamentally shifted our entire understanding of dinosaur behavior.
They really did. Because up until those excavations, the prevailing view of dinosaurs was largely that they were solitary reptilian beasts.
Like they lay their eggs and just abandon them.
Right, like modern sea turtles or something. But Egg Mountain changed everything, primarily through the discovery of a dinosaur named the Maiasaura.
The name translates to good mother lizard, doesn't it?
Yes, and the physical evidence demands that title. The fossil record at Egg Mountain is just astonishing.
What did they find?
They found massive, tightly packed nesting colonies. Thousands of individual animals building nests spaced exactly one parent's body length apart.
Oh, wow. Like modern penguins or albatrosses.
Exactly. They were nesting so closely they could incubate their eggs without stepping on their neighbors.
That paints a picture of a highly complex, vibrant social ecosystem. These weren't monsters. They were native life forms raising their young.
It was a thriving biological community. But the tragedy of Egg Mountain is that the only reason we know so much about them, the reason the nests, the fragile crushed eggshells, and the tiny skeletons of the hatchlings are so perfectly preserved, is because that entire vibrant ecosystem was annihilated.
They were buried alive.
Rapidly and completely. Entombed in multiple thick layers of volcanic ash.
Now, if you're listening to this, you might be thinking, okay, a volcano erupted and buried some dinosaurs. That happens all the time in geology.
Sure.
But we need to look incredibly closely at the details of this specific ash, because it is the smoking gun of the UTGH framework.
It is the absolute key to the whole theory.
So what exactly did Horner dig through to find these nests?
Well, the paleontological literature is very specific about the matrix encasing the fossils. It describes the burying material as a pale, white to light gray, fine-grained bentonite.
Okay, let's define bentonite for a second.
Bentonite is essentially volcanic ash, specifically volcanic glass and pumice that has chemically weathered and altered over time by interacting with water.
Right.
But the crucial identifiers we need to lock onto here are the visual and textural descriptions: pale, white to light gray, and fine-grained.
Keep pale and fine-grained in your mind, listeners, because it is about to become the center of a massive scientific dispute.
Yep.
Let's look at the geography first. Egg Mountain is roughly 350 kilometers north of the Yellowstone caldera. In human terms, that's a bit of a drive. In volcanic terms, how far is that?
It is point-blank range.
Really?
To understand the scale, the UTGH text asks us to look at a modern observable eruption, Mount St. Helens in 1980.
Okay, a highly destructive eruption most people have seen footage of. The whole side of the mountain blew out.
It was devastating, yeah. But geologically speaking, Mount St. Helens was a relatively modest event.
Modest.
It ejected approximately 1.2 cubic kilometers of material.
1.2 cubic kilometers.
Yes. Yet within hours of that eruption, the ash cloud traveled eastward and began blanketing eastern Montana, dropping measurable ash as far as 800 kilometers away.
800 kilometers away from just 1.2 cubic kilometers of ash.
Now scale that up to Yellowstone.
Oh boy.
The caldera-forming eruptions of the Yellowstone system during its activation phase didn't eject 1 cubic kilometer. They ejected hundreds, and in some phases, over 1,000 cubic kilometers of material.
So mathematically, a Yellowstone supereruption dropping a massive suffocating blanket of ash onto a dinosaur colony 350 kilometers away isn't just possible.
If they existed at the same time, it is an absolute physical inevitability. Yellowstone is the apex volcanic feature of the continent.
It is the glaring, undeniable suspect for burying these animals.
If you are an investigator standing in Montana looking for the source of a massive ash fall, Yellowstone is the only logical suspect.
Which brings us crashing into the 80 million year chronological wall.
Right.
Because if you ask a standard geologist if Yellowstone buried the Maiasaura, they will tell you it is impossible.
It is the ultimate alibi. Under the standard geological model, radiometric dating places the two Medicine Formation, the rock layer containing the dinosaurs, at roughly 83 to 74 million years old.
So the late Cretaceous period.
Exactly. But standard radiometric dating of Yellowstone's earliest eruptions places them at roughly 2.1 million years ago.
So you have a discrepancy of 80 million years.
Yes.
The standard model dictates the dinosaurs lived, thrived, and were buried 80 million years before the Yellowstone magma chamber even existed. The suspect has a watertight alibi.
It does.
So if Yellowstone is ruled out by the timeline, who does standard geology blame for the ash at Egg Mountain?
Because the timeline forbids Yellowstone, the standard literature is forced to look elsewhere. It officially attributes the immense volume of ash burying the Maiasaura to, and I quote, unspecified arc volcanics to the west.
Unspecified arc volcanics. That sounds suspiciously like a geological shoulder shrug.
It is a necessity of the timeline, really. They know the ash is there, they know it came from the west based on wind patterns, but they cannot point to a specific surviving volcanic caldera in the western subduction zones capable of producing that exact massive deposit at that exact time.
So they just point to a generalized region of ancient, extinct arc volcanoes.
Right.
If you're listening and thinking, wait, you can't just throw out 80 million years of radiometric dating just because you want to blame Yellowstone, you are right to be skeptical. I mean, it sounds crazy.
It does sound crazy.
But this is exactly where the UTGH framework transitions from a theoretical narrative into hard, falsifiable science. Darrell Waters proposes a strict logical test based on the physical chemistry of the ash itself.
He asks us to suspend the radiometric timeline for a moment and treat the ash like physical forensic evidence.
How so?
Well, imagine digging up an ancient Roman ruin and finding a perfect layer of modern Kevlar polymer buried beneath the cobblestones. You have two choices. Either the Kevlar was invented thousands of years ago, or your understanding of the timeline of that specific dirt is fundamentally flawed.
Right, you test the physical material to see what it is, regardless of where it was found.
Exactly. And UTGH applies formal if this then that scientific methodology to the bentonite at Egg Mountain.
Okay, let's walk through those steps. I am ready. What is step one?
Step one is the physical observation, which is undisputed by mainstream geology. The ash is a pale white to light gray bentonite.
Okay, observation locked. Pale ash. What is the first logical deduction?
Step two. If the ash is pale and fine-grained, then it must be a specific type of ash called rhyolitic ash.
Rhyolitic. I know there are different types of magma, but why does the color prove it's rhyolite?
It comes down to the chemical composition of the melt. Rhyolite is magma that is incredibly high in silica.
Okay.
When you have catastrophic melting of thick continental crust like a mantle plume burning through North America, you get high silica rhyolitic magma. When it erupts and shatters into ash, it is extremely pale, white to light gray.
Okay, so pale equals rhyolite.
Mm-hmm.
What's the alternative? What kind of ash do the unspecified arc volcanics produce?
Arc volcanism, which occurs at subduction zones where oceanic plates dive under continental plates, primarily produces basaltic or andesitic magma.
And what does that look like?
Well, this magma is lower in silica and higher in iron and magnesium, so when it erupts, the resulting ash is dark. It's dark, gray, brown, or black.
Ah, so this is a massive physical contradiction.
Sure.
Standard geology blames arc volcanoes, which produce dark ash,
Mm-hmm.
but the ash burying the dinosaurs is unequivocally pale.
Yes, the physical color explicitly points away from arc volcanism and directly toward a continental hotspot.
Which brings us to step 3.
Right. If the ash is rhyolitic, then it must come from a massive silica-rich volcanic system capable of generating that highly specific type of pale magma.
Which leads inevitably to step 4.
If Yellowstone is the only major rhyolitic volcanic system geographically capable of producing that immense volume of pale fallout within a 350-kilometer range, then the ash must be from Yellowstone.
Okay, I follow the logic chain perfectly. Kale ash means rhyolite. Rhyolite means continental hotspot. The only hotspot in range is Yellowstone. Therefore, Yellowstone buried the dinosaurs.
That's the logic.
But I have to push back here. A skeptic would argue that maybe there was a massive rhyolitic volcano out west that just eroded away over 80 million years. You can't upend the entire radiometric timeline of the planet just based on the color of the dirt. Color isn't conclusive enough.
You are absolutely right, and Darrell Waters actually agrees with you.
He does.
Yes, color is an indicator, but it is not definitive proof. The UTGH framework doesn't stop at visual identification. It demands a specific, hard chemistry falsifiable test. It argues that physical chemistry trumps the radiometric timeline.
This is the crux of the entire theory. What is the chemical test that proves this?
We have to move past major elements, like silica, and look at trace element geochemistry.
Trace elements. We were talking about elements that exist in just parts per million within the ash.
Yes. While the major elements make up the bulk of the rock, the trace elements act as a highly specific chemical fingerprint. They tell you exactly how and where the magma was formed deep within the Earth.
Okay, so how do we fingerprint Yellowstone versus an arc volcano?
It's a tale of two vastly different melting processes. Let's look at the unspecified arc volcanics first. At a subduction zone, an oceanic plate dives into the mantle.
Right.
It drags down massive amounts of seawater. This water fundamentally alters the chemistry of the melting process in the mantle wedge above it.
How so? What does the water do?
The presence of high-pressure water stabilizes certain minerals deep in the earth, specifically a mineral called rutile.
Rutile, okay.
Rutile acts like a chemical sponge for two specific trace elements, niobium and tantalum. It locks them away in the solid rock.
Oh, I see.
So when the liquid magma finally rises to the surface and erupts, it is starved of niobium and tantalum.
So arc volcanoes have low niobium and tantalum.
Yes. Furthermore, the water-rich fluids transport highly soluble elements like barium and lanthanum up into the magma.
Okay.
So the chemical fingerprint of an arc volcano is suppressed niobium and tantalum, elevated barium and lanthanum. This is universally known in geochemistry as the arc signature.
Okay, so that's the barcode for the standard model suspect. What is the barcode for Yellowstone?
Well, Yellowstone is a mantle plume. It originates from deep in the mantle, far away from subducting seawater. It is a massive, dry heat source burning through the crust.
So there's no rutile sponge.
Exactly. Because there is no subduction water to stabilize rutile, the niobium and tantalum are not locked away. They melt right into the magma.
So plume-derived rhyolite, like Yellowstone, is flooded with these trace elements.
Exactly. Plume rhyolites exhibit characteristically high concentrations of niobium and tantalum, as well as elevated zirconium, hafnium, and yttrium. That is the plume signature.
I see the genius of this test. You have two totally distinct chemical fingerprints. If you take the ash from Egg Mountain and put it in a mass spectrometer, if it shows low niobium and high barium, UTGH is dead. The standard model wins.
Correct.
But if it shows high niobium, high tantalum, zirconium, and hafnium,
Then the ash absolutely, chemically, incontrovertibly originated from a mantle plume. And the only mantle plume system capable of that deposit is Yellowstone.
wow. Has this test been run? Has anyone checked the niobium levels of the dinosaur dirt?
The UTGH text notes a fascinating and somewhat frustrating reality of modern geology. This specific targeted trace element comparison has rarely, if ever, been rigorously applied to the Egg Mountain bentonites in the mainstream literature.
Wait, why not? If the mystery of the ash source is unsolved, why wouldn't geologists just run the mass spec?
Because of the timeline. Under the standard uniformitarian model, the test is deemed irrelevant before it even begins.
Oh, because they already know the answer.
Right. If your radiometric dating tells you the dinosaurs died 80 million years before Yellowstone existed, why would you waste grant money testing the ash to see if it matches Yellowstone? The timeline dictates the questions you are allowed to ask.
It's circular logic. You trust the radiometric clock so completely that you refuse to run a chemical test that might prove the clock is wrong.
UTGH argues that we must prioritize the hard chemistry over the theoretical timeline. If the trace element chemistry points to Yellowstone, we must accept that Yellowstone produced the ash.
But if we accept that, we have to address the elephant in the room.
The timeline gap.
Yes.
Yeah.
If Yellowstone buried the dinosaurs, why do the radiometric clocks say there is an 80 million year gap between them? How can radiometric dating, which is based on the constant decay of radioactive isotopes, be that profoundly wrong?
UTGH introduces the concept of a radiometric artifact. Radiometric dating relies on a fundamental assumption that the rock has remained a closed system since it formed.
Meaning no parent isotopes or daughter isotopes have leached in or out of the rock over time.
Exactly. You need a closed system to ensure the ratio you are measuring today accurately reflects the time past.
Right.
But the UTGH framework posits a global rupture event. We are talking about the crust fracturing, massive decompression melting, and highly reactive supercritical water flushing through the Earth's upper layers.
A supercritical fluid, which we established is the ultimate solvent.
Yes. UTGH argues that this catastrophic environment, the immense heat, the kinetic friction, and the flush of highly pressurized chemical fluids completely corrupted the closed system assumptions of the crustal rocks.
So it messed with the isotopes.
It altered the isotopic ratios, artificially inflating their apparent ages. The 80 million year gap is not real time. It is a chemical artifact of the apocalypse.
That is a staggering paradigm shift. If we follow the physical logic, if the pale ash means rhyolite, and the chemistry demands a mantle plume, and the artifact explains the timeline, we arrive at a breathtaking conclusion.
We do.
The Mayasora and the Yellowstone megacaldera existed simultaneously.
They occupied the exact same geographical landscape at the exact same moment in time.
And if that is true, the physical excavations at Egg Mountain stop being just a record of dinosaur biology.
No, they become something much darker.
They become a horrifying frame-by-frame documentary of an ecosystem trying to survive a waking supervolcano. Let's look closely at the stratigraphy Jack Horner uncovered, because he didn't just find one layer of dead dinosaurs, did he?
No, he did not. The excavations at Egg Mountain revealed a deeply complex stratigraphy. They found multiple nesting horizons at distinct vertical positions within the rock.
Meaning layers stacked on top of each other.
Yes, a layer containing nests and eggs,
Yeah.
then a layer of barren mudstone, then another distinct layer of nests, then more mudstone, over and over.
And what material is separating or burying these nesting horizons?
The pale rhyolitic bentonite ash.
Okay, let's apply our if this then that logic to the biological narrative.
Very well. If Yellowstone was in its early post-rupture activation phase, the immediate aftermath of the thermal buffer being removed, then we know from volcanic physics that it would not just erupt once and go to sleep.
Because it's unstable.
Extremely. A massive, newly uncapped magma chamber is highly unstable. It would erupt repeatedly, violently over a relatively short geological window as the system attempted to achieve equilibrium.
And if it's erupting repeatedly, sending thousands of cubic kilometers of pale ash into the stratosphere, then we would expect to see exactly what Horner found in Montana, a rhythmic cycle of destruction.
The multiple ash horizons at Egg Mountain tell a desperate story of survival and site fidelity. Under the UTGH interpretation, the timeline of events looks like this. The Mayasora establish their massive nesting colony in a thriving environment. They construct their nests, lay their eggs, and begin incubating.
And then, the newly unleashed Yellowstone system detonates 350 kilometers to the south.
An eruption vastly larger than anything humanity has ever witnessed. A colossal column of superheated, pale, rhyolitic ash blasts into the stratosphere. Caught by the prevailing winds, this massive dark cloud drifts steadily north over the Montana landscape.
It blots out the sun, And then it
Yeah.
begins to fall.
It blankets the nesting grounds. And it's important to remember this isn't organic wood ash.
Right.
It is pulverized glass and rock. It is incredibly heavy, and it turns into a suffocating cement when it gets wet. The adult Maiasaura, being larger, stronger, and highly mobile, recognize the immediate environmental collapse. They flee the area. They survive the initial fallout.
But the young in the nests, they can't run.
Yeah.
The eggs can't move. The hatchlings are too small to wade through feet of volcanic glass. They are buried and suffocated where they sit.
The entire generation is wiped out in days.
The text paints such a vivid, heartbreaking picture of what happens next. The eruption eventually subsides. The ash settles. Over the next few months, or perhaps a year, seasonal rains wash mud and sediment over the thick ash layer, creating a new, albeit barren, surface.
Right.
And then the surviving adults return.
They return to their exact nesting grounds. This is a highly documented biological imperative known as site fidelity.
We see that in animals today, right?
We do. We see it in modern avians. Seabirds will return to the exact same cliff face or tiny island year after year, regardless of the conditions. The Maiasaura were driven by instinct to return to their ancestral home.
So they trek back across this devastated landscape. They reach the coordinates of their colony, but the ground is higher now. They scrape out new nests right on top of the mud that just covered their dead previous generation. They lay a new clutch of eggs. They try to start over.
And then the unstable Yellowstone magma chamber reaches critical pressure again. It erupts.
Another massive detonation. Another cloud drifting north. Another layer of pale ash burying the new nests. The adults retreat again. The new generation dies.
And the cycle repeats. Nest, erupt, bury, retreat, return. The pale bentonite ash interspersed with mudstone is not just a geological marker of deep time. It is a meticulous, horrifying record of every death of a generation.
The source text refers to it as a mournful precision. Under the UTGH framework, the Maiasaura weren't just random casualties of a slow-moving geological era. They were the very first witnesses to what the newly activated Yellowstone megacaldera could do.
They lived right on the edge of the apocalypse, desperately trying to raise their young in the shadow of a waking, repeating giant.
It entirely recontextualizes the paleontological site. Egg Mountain is no longer just a fascinating window into dinosaur social behavior. It becomes a high-resolution freeze frame of an ecosystem experiencing sudden, catastrophic environmental trauma.
It is the biological ground truth of a geological catastrophe.
Man, let's take a step back and look at the sheer scope of the journey we've taken today, because the implications of this deep dive are massive.
They really are. We started by questioning the very nature of plate tectonics.
Right. We examined how the UTGH framework uses the physical lengths of hotspot tracks, the 2,000-mile Reunion track versus the 430-mile Yellowstone track, not as a measure of millions of years, but as a direct mathematical speedometer reading.
Of tectonic plates decelerating from an incredible initial hydroplaning velocity.
Then we looked at the trigger mechanism for that kinetic event and the volcanic violence that followed. The violent expulsion of a 100-kilometer deep subterranean ocean of supercritical water.
The sudden removal of that global thermal buffer, causing instantaneous decompression melting of the Yellowstone mantle plume. Yellowstone wasn't just born, it was uncapped and unleashed.
And we followed the fallout of that catastrophic activation north to Montana. We applied a strict, falsifiable scientific method to the pale, fine-grained bentonite ash burying the Maiasaura colonies.
We use the logical deduction. If the ash is pale, it's rhyolitic. If it's rhyolitic, it requires a massive continental mantle plume. And Yellowstone is the only candidate in range capable of that volume.
Which brought us to the ultimate trace geochemistry test, the specific elemental ratios of niobium, tantalum, zirconium, and hafnium.
UTGH claims this chemical barcode can definitively falsify the standard 80 million year timeline gap. If the chemistry demands a plume, the radiometric timeline is an artifact of the rupture event, proving the dinosaurs and the supervolcano existed simultaneously.
And finally, we saw the tragic biological reality of that contemporaneous existence. The multiple stacked ash horizons at Egg Mountain, recording the repeated destruction of a massive nesting colony by Yellowstone's violent early phase.
A megacaldera birthed by the rupture of a subterranean ocean, its pale ash serving as the burial shroud for generations of native life.
What stands out to you as you listen to this? I would encourage you to consider how profoundly powerful timelines really are in science. When an entire discipline assumes a timeline is an absolute, unquestionable fact, it subtly shapes every single question they are willing to ask.
It can literally stop a geologist from taking a sample of dinosaur dirt to a mass spectrometer to test the niobium levels, simply because they believe the source volcano didn't exist yet.
It's the danger of assuming you have all the variables locked down. If you think the timeline is settled, you stop looking for the nuance in the chemistry. The UTGH framework, regardless of whether you ultimately agree with its catastrophic conclusions, serves as a crucial intellectual exercise.
It forces us to re-examine the foundational assumptions that dictate our interpretation of the physical evidence. Science requires us to constantly test our assumptions, especially the ones we consider unassailable.
And as we wrap up, I want to leave you with one final, deeply provocative thought drawn from the implications of the text. Something to mull over long after this deep dive ends. It builds on everything we've discussed about physics and momentum, but it points menacingly toward the future.
This is the logical endpoint of the deceleration theory.
Think about it. If the Maiasaura were buried by Yellowstone's early, highly violent activation phase, and we know that Yellowstone currently sits quietly under the state of Wyoming today, waiting, what does the ongoing deceleration of Earth's tectonic plates imply about the future of the Yellowstone hotspot?
Under the standard model, the plate just keeps creeping along at the same speed forever. But under UTGH, if the North American plate was moving fast and is now grinding down to a centimeter-scale crawl, the physical interaction between the plate and the hyperheated mantle plume is fundamentally changing.
Exactly. If the plate is slowing down, it is lingering longer and longer over that massive subterranean blowtorch. It's absorbing more heat in a concentrated area. So the question is the Yellowstone system truly going to sleep? Or, as the kinetic energy of the North American plate finally approaches absolute zero, is the mega caldera just reloading for something even worse?
It is a chilling physical deduction. If the blowtorch stops moving, the metal eventually melts all the way through.
Keep questioning the ground beneath your feet, because whether it's moving fast or slow, the forces beneath us are writing a story we are only just beginning to understand.